In module 2.3, we're going to cover conditional probability and Bayes' theorem. But before I do that, I want to briefly recap what we did in module 2.2. In module 2.1, we'd introduced probability rules, the rules for the probability of product of two events, or A and B event occurring. Then we discussed rule for addition of two events, or A or B occurring. And we looked at DeMorgan's law. And then we worked out in module 2.2, we had worked out a set of examples which included enumeration, estimating probability by enumeration, counting all the possible ways. And then we worked out an example on two dice, again, enumeration. The third example was also enumeration. And then the last example used the notion of complement, DeMorgan's rule, in order to estimate the probability that the player will hit at least once in 3 at-bats, the last part of the question. Now we're going to continue on, and we're going to discuss conditional probability. And if you recall, conditional probability, which is denoted as shown here, to be read as probability of event A occurring given that event B has occurred. By Bayes' theorem is probability that A and B will occur divided by probability of event B. So in other words, this is probability of A and B. A intersection B is to be read as A and B divided by probability that event B will occur. Similarly, one can ask what is the conditional probability of event B occurring given that event A has already occurred. Then the conditional probability is probability of A and B divided by probability of A, and this is Bayes' theorem. Okay. And using these two relationships, and you can also express it with the alternative notation here, using instead of A intersection B, you can write it as AB, A times B. Using these two relations, one can now express probability of A given that B has occurred is equal to probability that of B given that A has occurred times probability of A divided by probability of B. This is the statement of Bayes' theorem. This is the statement of Bayes' theorem. Now, if the two events A and B are independent, so then the occurrence of B has no relevance to probability of occurrence of event A if A and B are independent events. Intuitively, we would not expect any connection between B occurring and A occurring if they are two statistically independent events. Therefore, if the events A and B are independent, probability that event A would occur given that event B has occurred is independent of whether B occurs or not, and that's equal to probability of A. And therefore, one can also say that probability of event A occurring has no bearing on whether B has occurred or not occurred, which is complement of B. So therefore, probability of A given B is the same as probability of A given B complement, or B not occurring, and that's equal to probability of A if A and B are independent events. And similarly, if A and B are independent, probability of B occurring, the probability of A occurring has no occurring or not occurring has no effect on the probability of B occurring. Therefore, probability of B given A is the same as probability of B given A complement, and that's equal to probability of event B. Now we can generalize the conditional probability statements that we've seen so far for a situation that we see very often in practice. Let's say we have a failure event. Let's call this whole region denoted as F. Okay. And let's call this a failure event. And the failure event often has multiple causes, mechanisms, we would call them, failure mechanisms. So multiple causes. Let's label them as cause 1, cause 2, C1, C2, cause 3, 4, and 5, and so on. Failure causes 1 through 5. And often these failure causes are mutually exclusive. If one occurs, the other doesn't occur. For instance, in an automobile, I might have a tire flat that could cause the automobile to not run. I could also have a transmission failure, and those are two mutually exclusive causes. One usually, when one happens, the other doesn't simultaneously happen. Therefore, we can think of the failure as consisting of many causes, failure event as many causes, but they're all mutually exclusive and they bijointly, meaning that failure could occur either by C1 or by C2 or by C3 and so on. They're mutually exclusive, but they're all bijoint. So failure could occur by cause 1, cause 2, cause 3, 4, and 5, and so on. So in which case, we can write the probability of failure as the summation, remember using the summation rule, addition rule, except now all these events are mutually exclusive. Therefore, the intersection part goes away. And that's just probability of F times Ci. So probability of F is summation of probability of F times Ci, which now I can write using Bayes' theorem as probability of F given Ci times probability of Ci. This last bit comes directly from Bayes' theorem for the product of F and Ci, the event F and Ci occurring. What this basically says is that there are many causes Ci, and that can lead to potentially to failure. What we want in practice is probability that failure occurred by a specific cause. So in reality, what will happen is what we would seek is probability of Ci given F is what we would seek. In other words, when a failure, given that a failure event has occurred, we would want to know what is the probability that it occurred due to cause 1. Okay, given that a failure has occurred, what is the probability that it occurred due to cause 1 or cause 2 or cause 3 and so on? That's really what we seek in practice. But in a laboratory environment, much easier to characterize failure under an isolated cause. So in other words, we would look specifically at one cause and ask the question, what's the probability that the system would fail due to a specific cause? Okay, so we could, I'll work through examples to illustrate this notion, but it's important to keep in mind that this probability of failure given Ci is the situation in a laboratory, whereas in reality we would seek Ci given F. In practice, in a field use, not in a laboratory environment, but in a field use, what we would seek is probability of, given that a failure has occurred, what's the probability that it occurred due to a specific cause? And that can be expressed in the manner that's shown here. And this is how we would apply it in practice. Okay, so in the next module, I'll work through examples of Bayes' theorem, conditional probability statements. So this last expression, the utility of this last expression becomes clear.